Greetings to you all. My name is Fatima Garba Yusuf and this is Californians. And in this video, we are going to solve an example that encompasses all we've treated in previous videos. That's we're going to solve an example that has an aspect that contains identifying the faces present, the determination of the face compositions, and also the calculation of the relative amount of each face present, which will be in weight percentage. So consider this a lead tin system with 60 weight percent lead at two different temperatures at 200 degrees Celsius and 183 degrees Celsius. So we are asked to determine the faces present or the face present in each case, and then we are also asked to determine the face compositions and also the relative amount of each face present. Before we start diving into the calculations, let us first study this image well. Now, if you will take a look at this image, you will notice that it's a phase diagram with temperature at the y-axis and composition at the x-axis. And obviously, it's not a unary phase diagram since we have two components, lead and tin. And then we have a number of phases here. We have the L phase, which is the liquid, we have the alpha phase, and we have the beta phase. So here we don't just have a liquid and a solid phase, but we have an alpha phase, we have a liquid phase, and then we have a beta phase. So at the point where the temperature is quite high and at certain concentrations, we have the liquid phase. And at some other points, we either have the alpha phase or the beta phase or a combination of 2 out of 3 phases. For example, we have L plus alpha in the area that's in between alpha and liquid. That's a 2-phase area. Then we have another 2-phase area in between alpha and beta, which is the alpha plus beta phase. And then another 2-phase area that contains the L plus beta phase. So as you can see, this is a multi-phase diagram, and of course, like I mentioned earlier, it doesn't have to be just one diagram with just a single 2-phase area. Here we are having 3 different 2-phase areas, and it depends on the temperature we have and the concentration of our alloy for us to determine the composition, the phases, and also the relative weights. But then from the question, there's actually a tricky area. We were told that it's a lead tin system with 60 weight percent lead, but our x-axis actually contains the percentage of tin. So for you not to make a mistake, you have to actually understand that even though you were given the percentage weight of lead and your x-axis is that of tin, you can simply say that, okay, if 60% is lead, it simply means that the rest, that's 100% minus 60%, which is 40%, is tin. So you know that your reference point is 40%, as you can see, which is identified by the purple dotted lines. Then we take a look at the first instance where we're told that the temperature is, sorry, here's a mistake, it's supposed to be 220 degrees Celsius. So we take a look at the first instance where we have 220 degrees Celsius, as you can see presented by this dotted line going vertical. It's called a tie line. So if you're going to take this into consideration, we are going to draw a tie line from this point up to this point. And this will be a dotted line because it's not part of what we are going to take a look at. But the actual tie line is in between this boundary of the alpha phase and the boundary of the liquid phase, because the reference line falls in between them. This implies that the phase present in our first instance, in A, the phase is a 2-phase region, L plus alpha. That's the first answer. So we can say the first answer for the scenario A is L plus alpha. Then they asked for the phase compositions. The phase compositions is also not difficult. You simply trace down. Since it's a two-phase region, you will be having two answers. One for the C alpha, since it's an L plus alpha scenario, and the other for CL. And this, I repeat, is because the two-phase region falls between the boundaries of the alpha phase and the liquid phase. So the phase compositions are, as you can see from the diagram, to ease understanding, they were put in different colors. The C alpha is 17%, while the CL is 46%. Alright, now the trickiest part, of course, is the calculation of the relative amount of each phase present, and this is done, or the answer is calculated in weight percent. So this is where the lever rule comes in. As we mentioned earlier, there's actually a derivation of a lever rule in the previous videos we made, but a simple way for you to understand how to calculate a lever rule is to name your sections. And by naming your sections is, okay, we have a reference point at the center, and then you name the distance between your reference point and one of the boundaries. So here we named it as R and we colored it in blue. And this is supposed to correspond with our alpha, right? But remember that I said we're going to switch when doing the calculation. While the distance between the reference point and the liquid boundary is S. Now, if we start by calculating our W alpha, keeping in mind that we're going to switch values, even though R is actually obviously looking to be the value that corresponds with alpha in an apparent way, that's not the value we're going to use. We're going to use S for the other side. So our W alpha is going to be our distance S divided by the overall distance from CL to C alpha. CL minus C alpha. Our distance S is actually equal to CL minus CO, right? Divided by CL minus C alpha. Now when we substitute the values, our W alpha will be equal to 46 minus 40 divided by 46 minus 17. Okay, so we have 6 divided by 29. This will give you, if you divide 6 by 29, it will give you 0.207 or 0.2068. So 0.2068. If you convert this to percentage, it will be 20.68%, or it's approximately equal to 21%. There are two ways that you can go about it. You can either just subtract this 21% or 20.68% from 100%, or you follow the long method. So for this one, I'm going to follow the long method, while for the second example, I'm going to just subtract from 100%. So from the diagram, our WL is going to be the distance R divided by our overall distance CL minus C alpha. So our distance R is actually the same as CO minus C alpha, and it will be divided by CL minus C alpha. So when you substitute the values, you'll be left with 40 minus 17 divided by 46 minus 17, right? So 40 minus 17 will give you 23, and this will give you 29. And when you divide this will give you a value that is approximately equal to 0.79. And of course, when you convert this to percentage, it will be 79%. So you see, it's actually the same as saying 100% minus 21% gives you 79%. Now, for the second instance, we're told that we should calculate all this, or we should determine all these answers 1, 2, and 3 for a temperature of 183 degrees Celsius at the same reference point of 68% lead, which is the same as 48% tin. So we come down here and we say at 183% degrees Celsius, as depicted in the picture with the light purple line, it actually stretches and touches two boundaries, the alpha boundary and the beta boundary. Therefore, our two-phase region is the alpha plus beta region. So for the scenario B, our phase is alpha plus beta. Then when we are talking about the determination of our phase composition, we are going to calculate the composition in the alpha phase and the composition in the beta phase. For the composition in the alpha phase, we are going to trace downwards here. That will give us approximately 19%. While for the beta phase, when you project it downwards from the point of contact, you need to be very careful here. It's because I'm using a stylus, so it's not very straight, but here you can see that it's about 98%. So our C beta is going to be 98%. Of course, it's 10 here too. Then for the third question, where we are supposed to calculate our W alpha and our W beta in this case. So our W alpha is going to be here also. Our reference point still stands to be this purple line. Hence, we are going to calculate the distance between this. Let's call this P and call the distance here Q. So if this is P and this is Q, when we are calculating for W alpha, we are going to take the distance Q as our numerator, and when we are calculating W beta, we are going to take our distance P as the denominator, since we are interchanging. So for our W alpha, we are going to say it's equal to Q, distance Q, divided by the overall distance. So the overall distance in this case will be 98% minus 19%, right? So we have 98 minus 19, and our distance Q is actually 98 minus 40, which is still our reference point. Remember that this 98 is our C beta, while 19 is our C alpha. Those are the extreme points. So 98 minus 40 divided by 98 minus 19 is going to give us, for the numerator, it's going to be 48, while for the denominator, it's going to be 79. So we are left with our W alpha to be equal to 58. 98 minus 40 is 58, divided by 79. And this will give us 0.7342. This will give us 0.7342, which is equal to 73.42%. We can round down if you want to. Now, like I said, in this example, I'm going to simply just subtract my value of W alpha from 100% to get my W beta. So my W beta is going to be 100% minus 73.42%, 0.2658 in decimal, and 26.58 in percentage. So this is 26.58 in percentage. If I want it to be a whole number, this will be 73% approximately, while this will approximately be 27%. So with this, we've come to the end of this topic. I hope that you've thoroughly understood what phase diagrams are about. You've understood how to calculate your degree of freedom, the use of the lever rule, how to derive it, and how to use it to calculate your weight fractions, and many other things that we've covered in this topic. So wish you best of luck, and see you in subsequent videos and other topics. Thank you very much, and stay tuned. Don't forget to like, subscribe to our channel, and stay in touch by putting on your bell notification to get notified of subsequent updates. Goodbye.